Behold, the newest addition to the Breadboard synthesizer. What is it, you may wonder? What could it possibly be, you may ask? Well, it is an overdrive unit. So I downloaded this schematic from Tom Whitwell's site. He basically has got a module called a mini drive. It is sort of a overdrive distortion module, and as a key part it uses an incandescent bulb. Now I couldn't find which bulb he was using for it because there's many types, and you do actually need one that is very low power because it consumes enough power as it is. You also need one that is 12 volts. So I had a little bit of a search on the on the local market, and I did find, well, the lowest rated bulbs I could find were these car lamps, which are rated for 5 watts and for 12 volts. But yeah, they are 5 watts, so in a synthesizer circuit they're quite, chunky. Of course, I don't use it very, they don't actually end up using a lot of power in this circuit, but yeah, these work pretty well. They are for your car, but for me, they're for my synthesizer. Now let's take a more detailed look at the way this audio signal travels through this circuit, okay? First of all, there's 2 inputs. The difference between these mainly is the amount of attenuation that happens before it goes into the rest of the circuit. So you've got one that is slightly higher gain or receives slightly less attenuation beforehand than the other one. Then you've got potentiometer here. And this potentiometer is the drive potentiometer, which is the only control really on the module. And this you can use to control the level of the signal that goes into the circuit. So basically how hard you drive the circuit. If you've got the wiper of this potentiometer all the way down here to ground, all that's going into the circuit is 0 volt constantly. And because there's AC coupling at the back here, you basically get nothing, you get silence. But as you then move the wiper further up, you introduce more and more of the signal into the circuit. Now what happens afterwards, we've got some AC coupling happening over here. So that centers the signal around 0 if it isn't already. And then it goes into this big network of, we see some NPN transistors, a PNP transistor, some resistors and capacitors. What's happening here? Well, something. And then it gets output to these jacks over here. There is some AC coupling over here. There is no resistor to ground behind here, so I don't exactly get this. If I were to design this, I would probably put like a 100k resistor to ground over here, so that this results in a low-pass filter with a cutoff around, 1.5 hertz. But there's no such thing here, and I guess it relies on the input impedance of whatever you plug this into to filter it, which I don't think is very good design practice. But anyway, there is AC coupling because it passes through a capacitor and they block DC voltages, right? So what happens in this network over here, right? Now, I'm not 100% sure, but to me, this looks like a long tail pair. And this, to me, looks like a common emitter amplification stage. Now, I believe this module was inspired by the Mini Moog. And if you look at the schematics of the Mini Moog, you find this topology all over the place. It's long tail pairs as far as the eye can see. There's ones with NPN transistors. There's ones with PNP transistors. These amplification stages are all over the place as well. So I think this is just a sort of glorified amplification stage. Let's have a look at that. So the long tail pair, I won't go into the details too far, but essentially it's a differential amplifier. And it looks like this. And you can see this is, fairly close match over here. The input signal, the scaled down and AC coupled audio signal is going to travel into the base of this NPN transistor. and then it's going to also be output via the positive output of the long tail pair over here. So that's what you see happening over here. And then it travels to the base of the PNP transistor, which I think is a common emitter amplifier, which looks a little bit like this. And then whatever comes out of that is output to the output jacks, but it's also being fed back into the negative input of the long tail pair. And so there's sort of a feedback loop going on between these two, right? Like this amplifies the signal in some way, and this amplifies it even further. But then what's happening over here is also being fed back, and so there's an interaction there. But the main takeaway is that you get a massive amount of gain and some degree of distortion happening. Now, you can see some details that are different. For example, this resistor over here on the negative side is missing over here. I guess you don't need it because you're also not tapping off the negative output here. So I guess you don't really need it. I could be wrong about that. There's also this capacitor and resistor combination over here. I guess this is here to stabilize the output here. It just allows a small amount of current to flow through it, but not sure. If you remove this in simulation, it doesn't really seem to change anything. So I guess this is just here for stabilization reasons. As well as this 10 picofarad capacitor over here on the feedback path. I think this is just here for some, some filtering and to make sure that there's no like high frequency oscillations. The feedback path over here is quite interesting. Basically, you have a voltage divider here that scales down this circuit or the signal's intensity to, a couple of dozen millivolts only before it gets mixed in. But then there's this massive 220 microfarad capacitor that I really don't know what it's doing. It's a massive capacitor. I guess it might be doing some filtering, but it's really big. And I'm not really sure, it doesn't seem to see much voltage at all on the positive input. So, not sure what it's doing. But anyway, this network over here is applying a large amount of gain to the signal before outputting it. And by way of this drive knob over here, you can basically choose how hard you drive your input signal through this amplification stage. Now down here we've got, I will go through this fairly quickly. The only thing that's happening here is some voltage conditioning with an MPN common collector amplifier and another PNP emitter amplifier, a common emitter one. And that all goes into the base of this NPN transistor over here, which I guess is just being used as a voltage controlled resistor. As you feed in more voltage over here, the resistance between the collector and emitter drops, and so more current can flow through your lamp. This resistor over here as well, I'm not sure why it's in here. I guess it's maybe to limit the amount of current flowing through the transistor. I actually put a jumper here and completely bypass this resistor, so it seems to work just fine. Yeah, so just a quick comment. Do not use the jumper. Put some resistance in there. The transistor will burn through, otherwise it's very hot. So yeah, do put that resistor in there. Now back to this. What happens if we apply a large amount of gain to this signal? Well, you get something that looks like this. So let's imagine we are inputting over here in our input this 4 volt peak to peak signal over here, this dark green one, which has a maximum amplitude of 2 volts. And it's a sinusoid here, there's a sawtooth wave over here, but its maximum amplitude is no higher than 2 volts. Now, if we apply, let's say, a gain of 5 to this, the maximum amplitude will become 2 times 5 is 10 volts, right? And so our total signal will be 10 volts plus 10 volts peak to peak, right? So 20 volts. And it's basically made the signal 5 times as loud or intense. Now, if we apply even more to that, maybe a gain of 10 or a gain of 100, what you then get is something even more intense. So for a gain of 10, you should expect a maximum amplitude of 2 times 10 is 20 volts. However, this circuit cannot supply 20 volts, right? It's only got a 12 volt rail and a minus 12 volt rail. And so what ends up happening is when you get close to that, around 11.7, 11.8 volts, you actually start clipping the signal and it can go no higher. So your signal will then change its shape. Basically, when it's very close to the zero line over here, the signal will just look like a really loud version of the original signal. But then once it gets over, or anywhere close to this supply line, it will be completely clipped off. And the louder you make this signal, the more gain you apply, it will become even more extreme. And this you see here. So if I have originally, I start with a sine wave, which is just one frequency, right? A sine wave is just one perfect frequency. We call that the fundamental frequency of this sine. As we apply more gain, the signal will be more and more squared up, right? It will start to resemble more and more a square wave. And if we apply a ludicrous amount of gain, it will, pretty much look like a square wave, right? Now, a square wave contains all the odd harmonics, right? So essentially, what we're doing here is we're introducing progressively more odd harmonics, which, will make obviously the sound more, it will add a lot of high frequency content because all these harmonics become more and more audible. And so I think that's what the circuit is doing. It's applying distortion by basically adding lots of gain and making things clip into the supply rails so that you get a more squarish signal that contains a lot more upper harmonics. So I have now patched a triangle wave into the oscilloscope, as you can see, and I've also passed it into the circuit that's going to drive it into distortion. And if I drive it harder with the pot, it's going to get louder, and the light's going to come on. But have a look at the oscilloscope to see what happens. We start with a triangle wave, and then we get, hang on, let me turn this down. You can see that as we're driving it harder, we get a square wave, see? Now we're just getting AC coupled, so the tops are a bit cut off. Maybe I can... Nah. Anyway, I hope you found that enjoyable or interesting. Maybe next time, in the near future, I'll look at some more musical applications of this lovely distortion module.